What would it mean to say that the space-time is warped or curved or something like that? How would that express itself in mathematics? How would it express itself in things that we can measure? You all know the Pythagorean theorem, right? A squared is b squared plus c squared. The distance from here to there is square root. This distance squared plus that distance squared, and so on, right? Now, I'm just going to go to a little bit of equations that are on our page. All right? The way I wrote it on the sheet is ds squared, that's the distance between any 2 points in this space. This is called the metric, and you'll see that word over there. Will be this equation there? Like dx squared plus dy squared plus dz squared, whatever. dx squared, dy squared plus dz squared, and so on. When we're talking about little tiny little distances, we use that little d. All right? Imagine now that you have a space-time, not only space by itself. What would you expect to do to that formula if you now have a space-time? What should change? What's the simplest possible way that you can change that? Okay, and you'll see the answer on the page. But think about it for a second and then see if you get what you expect. ds squared, that's the distance between any 2 points in this space-time, will be, if we added a little piece here onto the formula for the time distance between 2 points. What do you see on the paper? The formula for the distance, right, has been generalized so that what you have is a combination. You have a dx square, a dy square, and a dz square, right? But you also have now a t. All right? So you see that equation there? Like dx squared plus dy squared plus dz squared, whatever, plus dt squared. So if you imagine here is, let's say, this point in x, y, z at this time, and this point in space-time is this point in x, y, z at another time, and with the distance between them is the physical spatial distance plus the time distance between the two. Exactly the same way to do with the Pythagorean theorem. What would it mean to say that the space-time is warped or curved or something like that? How would that express itself? All right, so the way that we would mathematically represent the fact that there is a curvature in this space-time is we'll change that equation that you have up there with the dx squared plus dy squared or dr squared, depending on which kind of coordinates you're using, and we put something in front of it. Okay, we're going to put a function of time in front of the r, and we're going to put a function of space in front of the t. All right, do you see that on your page? Right, we have something like this. We have ds squared, that's the distance between any 2 points in this space-time, will be, instead of just having a dt squared, let's say a dr squared, the distance in space and the distance in time, just like the Pythagorean theorem of x squared plus y equals t squared, that would be if you just had a flat space-time. If you have a curved space-time, what you'll do is you'll add a function of r over here, a function of r here, and a function of time over here. You have some kind of a mixing of the space and time, some kind of strange connection between the space and time. So you could have a function of time multiplying the distance between the 2 points, and a function of space multiplying the time distance between 2 space-time points. So if I say I'm standing over here at this position at this time, and half a second later I'm standing over here, then in a flat space-time, the distance between the 2 space-time points would be, let's say, 1 foot squared plus half a second squared, something like that. And take the square root of that. Okay, you need to use certain units and so on. But that would basically be the idea. Just like you took the x squared plus the y squared, you take the amount of time squared between the two, the amount of distance squared between the two, add them up, and that gives you the distance in space-time. If you have a warped space-time, you have this mixture. You have a function of r multiplying the distance in time, and a function of t multiplying the distance in r. So the distance between these 2 points is not anymore 1 foot squared plus 1 second squared. It's 1 foot times half a second squared plus 1 second times half a foot squared. Some kind of strange mixing of the two. And that's what will give you this kind of warped space-time. Okay, the geodesic of which will be this straight line. Now, what will these two terms do? This term, you can see, multiplies the distance between 2 space points. Without the space points moving away from each other, it's just changing the amount of distance between them. Where did we just see that before? Okay, I mentioned something like that before, where expanding universe, where the space between the galaxies is changing with time without the galaxies moving away from each other physically. Just the space between them is expanding. That's exactly what this term would do. It would cause the space between any 2 points to expand. This over here is exactly the one that gives this twist to the space-time, which we interpret as gravity. So in other words, in the general theory of relativity, when we write geometric, this piece in a certain system, in a certain solution, will give you basically just about everything that you expect from gravity will come out of this piece of the equation. And basically everything that you expect to see that has to do with the expansion of the universe will come out of this piece of the equation. This piece, again, determining how spatial distance increases with time. And this piece determining the relationship between the r and t parts, the x and t parts, that twist, that strange curvature that allows you to see gravity as a curvature of space-time. So all of gravity is a curvature of space-time, and in a certain model, it's included in this term. So we have here two very beautiful little functions that encode within them, in this model, two incredibly fundamental phenomena. Gravity, whether it's the gravity of the Earth towards us, or the moon and the Earth, or the sun and the Earth, or the galaxies being held together, or the galaxies concentrating in clumpings of galaxies and groupings and so on. Or if you're talking about the actual acceleration of the galaxies from each other due to the expansion of space.